Hi YouTube. Today I'll be sharing the details of implementation, the various algorithms and data structures involved in the making of our high-performance computing project, a parallelized image search engine by Team Tech Phoenix. There has been an exponential leap in the growth of multimedia databases, those that are operated by tech giants like Google, Yahoo, Bing, etc., and also millions of images are being published to social media websites each day. So just to search by image, it would require the algorithm to traverse through each and every image in the database, enormous databases. So this problem has to be addressed. So hence a problem statement is to develop a fully functional parallelized image search engine that effectively reduces the time of querying potentially millions of images, which is a highly sought after problem that the computer vision community faces as of today and is obviously extremely taxing in itself. Our objectives include parallelizing the involved sequential approaches by making use of multiple processors or cores on the local machine, also by experimenting with different algorithms and data structures, while still serving scalability, expandability, interoperability, and aggregation as our core design principles. So for this purpose, we have chosen the ImageNet LSVRC 2012 validation dataset for object detection with around 50,000 images of varying sizes belonging to 1,000 different classes in order to demonstrate the working. Methodology. We'll be covering the following contents in the due course of the presentation. So we are running our application on a local Flask-based environment, which is basically a lightweight Python web framework wherein we could work with HTML, CSS, and JavaScript on the front end and Python on the back end. We've used deep learning and machine learning frameworks such as TensorFlow, Keras API, sklearn, and the VGG16 submodule of Keras. We've made use of the multiprocessing library majorly, NetworkX for managing and curating graphs, and other modules such as NumPy, SciPy, and Pillow. So we've performed the feature extraction using VGG16 model both serially and parallelly, and it took about 6 hours for the serial implementation and pretty much the same time, around 5 hours 45 minutes for the parallel extraction. VGG16 is a well-established object detection model, in fact also considering how it achieved 92.7% test accuracy in ImageNet Challenge, that is, the same dataset we're using right now. It was the first runner-up in the same challenge. So we performed the feature extraction on the fully connected layer, or the last but one layer, not considering the softmax layer of 1,000 nodes in a total of 16 layers. That's how the name came from. So we've used a VGG16 module from Keras by downloading the model weight from the internet. So coming to how we did the pre-processing, we initially resized the images to 224 cross 224 cross 3. We asserted them to 3 channels or RGB colors, extracted the pixel array, expanded dimensions by including the badge dimension, subtracted average pixel values, pre-processed input using the VGG16 submodules method, and also reduced the dimension, remove the badge dimension, and then we normalize the features. It's a typical feature extraction that is also given in the Keras documentation. A few challenges that we faced are that the VGG16 feature extraction part is pretty slow, and even when you consider the actual model, it took about 2 to 3 weeks while being trained on NVIDIA Titan GPU, and also when the extraction is done, it is extremely immobile. It occupies a lot of space and it's pretty inefficient. The feature vectors that we exported took about 800 MB space. Also, there are about 138 million parameters in the model that explains why it's pretty inefficient in terms of space and time. Also, we were facing TensorFlow memory allocation error, which was resolved after troubleshooting. The thing we did was to migrate to Windows subsystem of Linux, WSO, Ubuntu. So this is the analysis that we performed earlier for serial implementation and parallel implementation with varying core sizes of 2, 4, and 8 on 9 different images. We have averaged their times of execution and tabulated the same, and the same has been illustrated in the clustered bar chart as well. So the observation is that the time taken by the server 4 or the server with 4 cores is the least on an average, followed by server 8, and then server 2, and finally the serial implementation. So clearly the implementation with 4 cores is performing pretty well. The one with 8 cores isn't ideal since the system is having 8 cores, and obviously all the cores can be assigned to a single process when the other applications are in use. So that's where the difference is arising, else it would have been the 8 cores first, then followed by the rest. Since the square Euclidean distance is computationally expensive, we decided to also check out Manhattan distance, but surprisingly there wasn't a noticeable difference using the same, except for the decrease in visual accuracy. That could be because of the fact that we're using an optimized inbuilt implementation, np.linealg.norm for Euclidean distance, and there isn't one for Manhattan distance, and it requires us to do some sort of vectorized list comprehension. So we decided to use SciPy spatial.distance module's inbuilt function, but the time taken wasn't affected a lot. So we decided to stick with Euclidean distance since it's better than Manhattan in terms of accuracy. So until now we have used the standard nearest neighbor algorithms, but then these are extremely taxing and they could be computationally expensive depending on the size of the data set since it requires indexing of each and every image and computation of distance and sorting. So we decided to stick with the approximate nearest neighbor algorithms. Some of these include locality-sensitive hashing, which requires us to curate a hash function specifically uh, for the problem, and space partitioning includes us recursively performing partitions. It could either be in a standardized way or in a randomized fashion. So we decided to stick with clustering and graph traversal. So we went with k-means clustering, which is a well-known partitioning clustering algorithm, and it's in fact a hard clustering algorithm, and we chose k equal to 1000 since the number of classes in the data set are 1000, and we performed a principal component analysis using sklearn.decomposition module with the top 100 important features. So then we performed k-means clustering on these reduced features using sklearn's cluster module, and then we exported clusters as a dictionary with the keys as the centroid labels and the values as all the images in that particular cluster. The time taken for PCA was just around 2 minutes, and the k-means took around 45 minutes in total and was done serially. The clustering approach involves computing average distances of the first 3 images in each cluster. Since we're already having the clusters at this point, we sorted the distances, selected the top 4 cluster indices, computed and sorted the distances from the top 4 cluster images parallelly using 4 cores of the multiprocessing library. We returned distances and the image paths, and the clustering approach reduced the computations by 15.625 times, slightly compromising on the accuracy, and on an average it took about 3,200 computations, whereas the previous approaches had 50,000 computations in total. So we've also performed the graph traversal, and we've explored different options, such as the first one being Azure Cosmos DB, which is a specified service in Azure for managing non-relational databases, could be non-structured or structured. Gremlin API is specified for non-structured databases, specifically graph databases, but then it incurred costs and it required us to do everything from scratch, and it also required us to learn a few tech of Azure. So we ruled that out. We also wanted to go with the standard data structure implementation, which involved of defining a graph class. Here we are also using an undirected graph because if one image is related to the other image, then the other image would also be related to the first image. So it's an undirected graph by default. But then if you're trying to maintain pointers like next pointer, previous pointer, and there would be we were compromising on random access, and storing the pointers and traversing through them could be difficult. So since we've also ruled out the second option, we went with the Network X Python module, which is a curated module for managing and creating graphs and playing around with them. So there are also 2 things we could have done, which is a manual approach and automated approach. So in fact, we've also started with the manual approach. It required us to do everything from scratch, and it also required us to cut down the data set size, but it was time taking, so we went with the automated approach. So this is how we automated the graph. So the graph which we took was, it was an undirected and unweighted graph. A weighted graph is the one which is usually used, but we went with unweighted graph. since it will reduce the complexity of managing weights and dealing with the same. So the first thing which we did was since we are already having the clusters, we made each and every point in the cluster fully connected. So that would be NC2 points. So selecting 2 points out of n points. So that would be the number of collections. So if we sum it over each and every cluster, it would be the summation over n into n minus 1 by 2, which is around 13 lakhs. And the second thing which we did was right now we're having an incomplete graph wherein traversing from one point to the other point may not always have a path. So for each pair of possible clusters, so we're having 1,000 clusters. So if you pick any two pairs, that would be 1000 C2, which is 499,500 pairs. So what we did was we traversed to each and every image of the first pair, first cluster in the pair and the second cluster in the pair, and then we computed all the distances between each and every possible pairs, and then took the top 5 closest points between these clusters. So the number of connections is 5 into the number of possible pairs, which is around 24 lakhs. And it took about 6 hours to complete, wherein the initial one didn't take a lot of time. It took negligible time. And the number of edges are around 13 lakhs plus 24 lakhs plus 1. 1 being since for the purpose of dealing with the library with ease, we also included one extra edge from 0 to 1 because initially we're only having edges from 1 to 50,000. So that's another edge. So it took about 38 lakh edges, and the number of nodes is 50,000 plus the 0th node, which is 50,001. And the entire storage took about 5 Excel sheets since the limitation on Excel is about 1.048 million. So the initial part of the graphical approach that we used is quite similar to the clustering approach, wherein we computed average distances of the first 3 images in each cluster. So we sorted the distances like the topmost index, where in the earlier one we took the top 4 most indices. Here we only took the top first cluster index, and we performed breadth first search traversal BFS for the first image in this cluster. We computed and sorted the distances for level 1 and 2 nodes, and we returned the distances in image paths. So for level 1 nodes, we used a core of the CPU, and for the level 2, we used another core of the CPU. This is the computational time analysis of servers, the updated one to the previous 4 servers, including the clustering, graphical, and graphical optimized technique. The graphical optimized technique is the same as the graphical technique just discussed, but it only involves the importing of all the already exported BFS distances of level 1 and 2, since we already know that we're going to anyway traverse through every possible first image in each of these clusters. We've made a point to export it as an optimization. The same is illustrated as a clustered bar chart. Conclusion and future work. Results and conclusion. The proposed architecture satisfies the pre-stated objectives, and we have seen a noticeable difference in the serial and parallel implementations as illustrated earlier. We've optimized the existing architecture using clustering, graphical approaches as illustrated earlier. So the architecture is a lightweight and extensible architecture, and it has a great visual accuracy. A future scope includes developing a prototype that works on a million scale. We want to work and develop on other approximate nearest neighbor search algorithms and optimize our graphical approach as well. We want to utilize the cloud compute services to perform the same. References. These are a few literature references that we have made use of during the due course of the project. These are a few web references. Thanks a lot for your valuable time. You may find the source code and a demo of implementation in the description box below. Thank you.